Hi, everybody, and welcome back to the Rule Your Pool podcast. I'm your host, Eric Knight with Orenda. This is episode 104. And it's feeling really good that we have more listeners than episodes now, so keep that up. Go us. Go you. If you're new to the show, thank you for being here. Normally, I have somebody on here to talk to, like Jared, or last week we had Sean, but getting people available while we're still in trade show season, it's laughably impossible. So I'm doing this one alone. And in this episode, I want to talk to you about crystals, but not the type of crystals we've talked about before. In the past, we've talked about calcite crystals, which are calcium carbonate, or we call them winter crystals. These are the crystals that pools that are winterized sometimes open to, and they think it might be scale, but they're not scale. They're the opposite of scale. Calcite crystals we've talked a lot about. We've had articles for years, but in the process of researching for those articles and asking people for photos of crystals in pools, we were getting some photos of these beautiful crystals, and we didn't know any better, so we were including it with calcite crystals. But come to find out, they are not the same thing. And in today's episode, I'm going to introduce to you a new calcium compound that you may not have heard of before. And it's not a very common issue, but depending on where you live, it might be. In this episode, we're talking about calcium sulfate. Let's get into it.
Welcome to Rule Your Pool, the podcast by Orenda that explains and simplifies pool chemistry so that anybody, regardless of experience, can understand it. I'm your host, Eric Knight, bringing clarity to these subjects so that you can bring clarity to your water. If you're ready to rule your pool, then let's go.
I think taking a step back for a little bit of context would help. Pre-COVID, all those years ago, they kind of blend together. I was in the Northeast visiting some customers who had scale issues. They would open up their pools in the springtime and, oh my gosh, we have calcium everywhere. It's scale. You put acid on it, it goes away. It must be scale. Well, it was calcium carbonate, but it was not scale. As we've talked about in other episodes and in videos and in our blog, calcite crystals, we found out through lab tests, are the opposite of scale. They actually grow out of cement. And the way we knew they weren't scale was actually from photographs, not lab testing. The photographs were showing these crystals were on cement surfaces only. Like they were only on the tile grout, but not on the tile. They were only on the cement, but not on the pebbles. They were not on light fixtures or plastic fittings. No metal handrails. But it was on all these cement surfaces. And that told us these things are growing out of the cement because scale is blind. Scale can't just choose to only land on certain surfaces and not others. Because the defining line of scale of any kind is an oversaturation of a mineral compound. We'll use calcium in this case. Of a calcium compound that precipitates out of solution because of an oversaturation and it lands on surfaces and hardens. That's what scale is. Now, the overwhelming majority of scale that we see is calcium carbonate scale. Calcium carbonate equilibrium, of course, is measured using the Langmuir Saturation Index, the LSI. We talk about it all the time because the LSI is what water cares about. But calcium carbonate is not the only calcium compound that we have in water. When we were talking about calcite crystals all those years ago and we were asking for photos and samples and people all over the country, we were getting so many photos. It was awesome. Thank you for that. But we were getting some of these crystal photos that just looked amazing, like different from all the other ones. All the calcite crystals were either long and pointy, but they were kind of ugly, stalactite-looking things, and they weren't symmetrical. They were whitish or gray. Nothing pretty about them. Scale's ugly. Calcium carbonate is not an artistic substance, I should say. I'm using the word artistic. I hope you know what I mean. It's not pretty. It's not naturally pretty. But these crystals that I'm referring to, they were different. They were geometrically gems. Straight lines, rigid angles, sharp. They looked like they were designed. But at the time, we just got excited because we didn't know the difference. We thought, hey, it's just another type of crystal. We haven't sampled it, but it must be the same thing. Or at least we didn't have any evidence to the contrary. Well, come to find out, they are not the same thing. And we didn't find that out on our own. We had help. So I'm going to give credit right now where credit is due. On Balance called us about that article, Kim Skinner and Q Hales, and said, hey, you've got pictures in there of calcium sulfate scale. And calcium sulfate, when it scales, forms crystals. Well, that was the first time I'd ever heard of calcium sulfate, but they knew about it because they're on the West Coast and in Tucson, Arizona, where this is actually a more prevalent problem. In fact, they had done quite a bit of research about it. It was news to me, and you don't see this in the Northeast very often. At least, I don't think I've ever heard of it. If you have this issue in the Northeast, I'd be stunned. But in Arizona and Las Vegas and Palm Springs, these desert areas that get really hot, dry climates with a lot of evaporation out of swimming pools, this is a more prevalent issue. And when I looked closer at the photos, I realized they were right. These crystals were different. Not only did they look different, these crystals were on top of surfaces. For instance, these crystals were on top of lights and plastic fittings and metal handrails and tile. They were even above the water line in some of the photos. How does that happen? Water has to pull calcite crystals out of cement, but these crystals were landing on things, which means they were scale. But I know that calcium carbonate doesn't form scale like that. Calcium carbonate just kind of slops on. It's ugly. These were beautiful, in my opinion. And the thing about these crystals is they're very hard to see when they start. They're very small, almost transparent, and they're sharp. They're like broken glass. Some of the reports we get are they're on the top step or on the sun shelf, and kids are cutting their feet, or dogs are cutting their paws. It's brutal. Like, if you look at this stuff, we have a photo of it in our blog, it's really hard to see until it gets bigger. And then it grows and it grows, and it gets a little bit more opaque, and then you start to see it and realize, oh my gosh, I've got a problem. So we knew we were dealing with a different substance. And thanks to On Balance for telling us that. That put me down the rabbit hole. But to be honest with you, that was pre-COVID, and then we got busy and I tabled it. I never forgot about it, but I tabled it. Fast forward to last year, we started getting calls about these crystals. And it jogged my memory of like, wait a second. Yeah, we have heard of those. We do have some photos. And people started sending in photos. Lo and behold, all these pools were, once again, Las Vegas, Phoenix, Lake Havasu, Arizona, Tucson, Palm Springs, California. They were all in the Southwest. They were all in the desert. They all shared a few things in common. Dry climate, high evaporation rates, and these crystals. So what is calcium sulfate? I think we need to dive into this. Calcium sulfate is an insoluble calcium compound that can form sharp crystals on surfaces underwater. Now, this is a type of scale because it comes out of solution with an oversaturation, but it is not dictated by the LSI. Remember, the LSI just does calcium carbonate, so this is a different compound. We've been researching this for a blog and for this podcast, and we found quite a bit of research. Apparently, this is a well-known substance, even though it was new to me. Calcium sulfate has three main forms, or they're called hydrates, that you find in nature. Gypsum, which is calcium sulfate dihydrate, is the most common. Then you have basanite, and then you have anhydrite, which is also called plaster of Paris. Okay, point is, this gypsum, this calcium sulfate dihydrate, that's what we think we're dealing with in pools. Now, I say think because I have not personally lab tested any of these samples. I'm going on the word of On Balance and other people that have known what they're talking about. For instance, there was a homeowner who called. He was a retired chemist. You know who you are. Thank you, by the way. Calls me up and says, hey, I saw your article on the Orenda website. I was Googling because I had crystals in my pool. But my crystals are gypsum. I was like, gypsum? I've heard that term. I think it's in my lawn product, like my fertilizer. Gypsum. Yeah, cool. Another type of crystal. That's crazy. So when he sent me the pictures, I said, wait a second. I've seen these photos before, and I referenced, in my computer. Wait, these are the same ones that On Balance showed me, basically. This is the same issue. A quick search of the interwebs told me that I'm an idiot, and gypsum is calcium sulfate dihydrate. Okay, so we know what we're dealing with. But this chemist, thankfully, was telling me, yeah, the way you get rid of gypsum is with a high pH. It precipitates at a low pH. Really? Well, that's the opposite of calcium carbonate scale, isn't it? The higher pH would drive calcium out of solution thanks to the LSI. But with calcium sulfate, it is a lower pH, which actually plays in perfectly in the hands of why Q Hales, in this article in Aqua Magazine, published in 2014, was unable to get it to budge with regular muriatic acid. Now, as an aside, if you read this article, you will notice that Q did something in here. Q, if you're listening to this, I would love to know where you came up with this idea, because it's nuts. Q decided muriatic acid isn't doing it. I'm going to boil muriatic acid and see if that does anything. And sure enough, it did something. I don't know how effective it was, but I'm less concerned with the results of that experiment as I am with how did you come up with the idea to take the most dangerous chemical we deal with in swimming pools and boil it? It's lost on me, but okay. Wow. Yeah, what an experiment. But the point is, acid does not clean it up. These crystals cannot be removed, which kind of plays into our hand of proactive pool care, because the best way to stop this from happening is to prevent it from happening in the first place. But how do we do that? Well, in order to do that, we need to understand, where do sulfates come from? Because we don't actually know an exact formula or threshold of when calcium sulfate precipitates. I don't know of an index like the LSI for calcium sulfate saturation. I don't think it exists. But at some point, you have enough calcium hardness, enough sulfates, a high enough temperature, and a low enough pH. That much we know. But at what point, we don't know. And nobody seems to know. I've scoured the internet for this. I've looked at peer-reviewed journals. Nobody actually, that I've found, has shown, well, you need this exact proportion of calcium relative to this proportion of sulfates at this temperature. I haven't seen anything like that. But the point is, you kind of need all of those things to create this perfect storm. Or you need water that's evaporating rapidly. Because if you have hot water evaporating, like in Arizona or Las Vegas, that water leaving lowers the amount of water, so the saturation of sulfates and calcium rises rapidly. This explains why calcium sulfate is usually right at or above the water line. It's because of evaporation. Now, I have seen it underwater. I've seen it on steps. I've seen it in spas, like indoor commercial spas that are heated, that are using dry acid. So we know it can be done, but you have to have enough of these things to happen. So where do sulfates come from? That's the question. How do they get into our water? Well, in these areas, sulfates do exist in drinking water, and depending on where you live, especially if you're on well water, you can have it. Water matriculates through the soil column, gets down into the aquifers, and you pull it out, you could have sulfates. If your city does not filter those out, then they're going to be in your drinking water. And if you do have sulfates, by the way, you should get a pre-filter and pull them out before they get into your pool or your drinking water. Just like nitrates, you don't want these things in your water, and they can be filtered out. But let's move beyond tap water for a second. Let's assume you don't have sulfates in your tap water. Well, you can still have this problem, because there are a lot of pool chemicals that contain sulfates. How about some examples? Sulfuric acid, or dry acid, which is sodium bisulfate. How about non-chlorine shock, potassium monopersulfate? Or how about a copper algicide, copper sulfate? Or a chlorine neutralizer, sodium thiosulfate. You get the point? Sulfates are in a lot of the products that we use already, and we just didn't realize it. But these sulfates don't go anywhere. Now, according to the UK's, let's see, what is it called here? The Pool Water Treatment Advisory Group. This is like their commercial pool model aquatic health code, so to speak. It's actually pretty good. They've got an article on here that we cite in our blog that says sulfate attack is a thing. It's corrosive, basically. So if you have over 300 milligrams per liter, that's parts per million, you can get degradation of concrete and other materials like metals, mainly concrete. So cement finishes. Well, I don't want that, but that's not even directly related to the LSI. That's sulfate doing that if you have enough of it. Sulfate corrosion also compounds itself when you have chlorides in the water. I'm just going to quote the EPA here, which we have in our article on muriatic acid alternatives, talking about sulfates. Sulfates and chloride corrosion specifically. And I quote, "In some cases, sulfates seem to aggravate the effects of chlorides. Chlorides present in the amounts as little as 0.3% with sulfates present can produce severe corrosion." This is from the EPA. That should tell you, hey, I probably shouldn't be using dry acid as my primary acid all year long, unless you're diluting regularly. Common theme with most of the pools that have reported these crystals to us. Now again, this is only people who reach out and tell us. They're almost all using dry acid, sodium bisulfate. To give you an idea of how fast sulfates accumulate, 1 pound of sodium bisulfate acid leaves behind 9.6 parts per million of sulfates in 10,000 gallons of water. Yeah, that adds up when the threshold is 300. It's kind of like using trichlor and not figuring out why your CYA is climbing. Well, that's because 1 pound of trichlor puts in about 6 to 6.5 parts per million of CYA per 10,000 gallons. Well, how about sulfuric acid? Sulfuric acid per gallon leaves behind 47.1 parts per million of sulfates in 10,000 gallons of water. 47.1. Now, granted, you're not using a full gallon at a time because you're making smaller pH adjustments, but that's a lot of sulfates, and they don't go anywhere. And eventually you get enough of these at a high enough temperature, in the right conditions, and a low enough pH, like an acid product. And you're going to get calcium sulfate. You know the other place we're seeing this is in commercial pools. Specifically, commercial pools on Cal Hypo that have a dry sodium bisulfate feeder. Yeah, in the plumbing right after that sodium bisulfate feeder, you start to get calcium sulfate crystals, calcium sulfate scale crystals. And it's brutal because remember, the low pH forces this stuff to precipitate. So this homeowner tells us the way to soften it is to use a high pH. Counterintuitive, but when I was in Tucson last, I visited Q, and we tried it. And it turned the crystals into sort of a gel. It definitely softened them. It made them easier to remove, but it didn't remove them completely. It's not like they just disappeared like if you put muriatic acid on calcium carbonate. They didn't just fizz and go away. But at least it's a sign that something can be done. So how do we prevent calcium sulfate crystals? A, limit the sulfates in your water to begin with. If you have high sulfates, drain and dilute, or use reverse osmosis filtration if that's not an available option. Number 2, chelate your calcium. Make sure that it is bound up and not able to bind to sulfates if you may have them. Number 3, stop overcorrecting with acid. This goes not just with acid dosing, and it's really how you add it. Don't column pour it. Don't put it down to the main drain so it can go straight into the equipment, like mainlining acid into the equipment, because that's going to be a very low pH at the filter and at the heater. Don't do that. What you want to do is you want to always measure your acid, dilute it, and let's not be correcting too low. We talk about containing pH. Containing pH does not require you going below 7.6 pretty much ever on a residential pool if there's cyanuric acid in the water. Now, if there's no cyanuric acid in the water, that's a different question. But if there is, you don't have to correct the pH as low. The point is we're adding too much acid, and that is part of the problem. High sulfates, high calcium, high temperature, low pH, too much acid. If you can decide, I love bringing that word back into it, decide, kill off the options and make a decision, commit. Remove factors from the equation. Decide to account for sulfates. Dilute them, keep them low. Decide to not use products often that contain sulfates. I'm not saying you can't use them. There's a place for a non-chlorine shock, for instance. But it's not all the time. It's not every week. I recommend going away from dry acid as your primary acid unless you have no other option. And if you don't, dilute water. It should not be used in Arizona. It should not be used in Las Vegas unless you want to face this issue, which, it's up to you. If you're using Cal Hypo as your primary chlorine, dry acid is probably not a fit for you. Neither is sulfuric. You should be using muriatic acid. So these are things that you can do to just limit the ability for your water to get into this perfect storm to cause these crystals to begin with. I hope this helps. I hope you don't have this issue. But if you do, check out our website. Just go to orendatech.com, search the word sulfate, and you will find several articles where we bring this up with pictures. If that looks like something you have, read the suggestions in that article or share this episode with someone who you think might have this problem. I'm Eric Knight with Orenda. I did my best. I don't think I did great, but I didn't have Jared to comparatively make me feel better about myself. So, it is what it is. I don't know what we're talking about in the next episode, but I'm sure it's going to be mediocre at best. Thank you so much for listening. It means the world to us. And by the way, in all seriousness, those of you who have come up to us at trade shows or given us a call that said you listen to this podcast, it really means the world to me personally, because I put a lot of work into this podcast. It is something I look forward to. Don't get me wrong. This is like the highlight of my week when I have time to do it. So thank you for continuing to listen to it. Thank you for sharing it. And like I said, I don't know what we're talking about next week, but hopefully it's better than this. Take care, everyone.
Thank you for listening to Rule Your Pool, a podcast by Orenda Technologies. For more information on what we discussed in this week's episode, check the links in the description or visit www.orendatech.com.
I hope you find this show valuable enough that you tap that subscribe button and share it with your friends. You can also like us on Facebook and social media. And with our help, you'll be able to rule your pool without over-treating it with chemicals and wasting money. I'll see you next episode.